stream is live, right? Okay, I'm sending the link. Okay, for this.
Can I take a picture of that and
It's fine, it's fine. Recording?
I don't think it's the I'm Mr. Sneeze and
You send it. It's fine, it's good. Just make sure that it's recording. Okay. Where's Vedant? Vedant. You want to ask him to play the video, right? Like.
थोड़ा सा उधर रख दे मुझे एकदम से I will have to suddenly get up and
Ma'am, the problem is people are coming in this way now, they cannot touch it.
I'll go out carefully.
Yes.
Have you heard this recording yourself?
Yeah, it's fine. The audio is always fine.
Good afternoon, one and all. I would like to welcome Dr. R. Vijayaraghavan, our faculty members, and all the students to this third and final day of Popli Memorial Series. We conducting the memory of Popli. We'll be continuing the discussion on quantum computers and qubits today. Yesterday we mentioned we have a Q&A session, so we'll be conducting that after this talk. So we'll take a combined Q&A session for this talk and this talk. With that, I would like to call Mr. R. Vijayaraghavan for
Thank you and welcome back for the last lecture. I got a little feedback that people at the last row are not able to hear me. So if you're not, just raise your hands so that I will increase my. Usually I'm quite loud. Alright, so and as he said, we will do a combined question answer session. So I'll try to finish a little early today so that we have time. I might go a little bit faster than the last 2 days. So today I'm going to be talking about this intermediate topic about what a quantum computer is useful for. Of course, I cannot cover everything. We will go through a few examples. But the first one I'm going to start is actually the idea of error correction. So it's not technically under this topic, but it's a very crucial step which is needed to make all of these machines useful. As I explained, these systems are unstable and they remain stable only for a short period of time. So all your computations have to finish currently in a time much shorter than that time scale, so that you are reasonably sure that the quantum computer has not experienced one of those decay events and completely randomized the output. Okay? So you have to do something to improve that. So one way, of course, is to make all your systems more stable, or invent a new physical system which is more stable. But you can only do that up to a certain extent, because these systems typically will coupled to some noise source and hence undergo these decoding processes. But luckily, people a while back, in fact, had figured out that it is possible to do something called error correction, where you can preserve a quantum state even though the individual components are still experiencing change. So that's the first topic we're going to discuss, and I'm going to go through that in a little bit of detail with a simple example, and hopefully that will make it clear why this works, even though it seems like it shouldn't work, and how quantum entanglement really plays a role. So anyway, I'll move on forward. So before getting into quantum error correction, I want to say a little bit about classical error correction so that you're oriented on what I'm actually talking about. Like, what does it mean? This is not actually a mysterious subject at all, right? So imagine two people talking to each other, and here it's shown as this wire phone, but when you talk to a customer service representative or something, and you're trying to say something, you might be saying PPT, but they hear BPP. This is because there is some noise in the channel where the clarity of the information you are trying to send is not is preventing the person on the other side to interpret what you are saying incorrectly. If I now translate this into the binary language, then essentially what I am saying is that if these two parties who are exchanging information and they are sending a string of binary digits, then because of noise in the system or noise in the channel you are transmitting, essentially what can happen is that one of those digits could get interpreted incorrectly. So in binary it's very convenient because there's only one type of mistake that can happen. A 0 could be interpreted as 1, or a 1 could be interpreted as 0. There is no other possibility, right? These are only two things which are allowed, so you have to interpret one or the other. So that's the mistake that can take place. And this can happen either on a communication channel, or it can happen in a stored system, a memory which you have, and over time, because of maybe somebody scratched your hard disk or your CD, and the system then read that incorrectly, right? And for qubits, this is a problem that you just wait, and everything just goes back to 0. So that's what's being represented here. So how do we work around this in our classical world? Because these are actually real problems. Right? So when we talk to people on the phone, we use something like this. We say, okay, P for Pune, P for Patna, P for Trivandrum. Then it's very clear, because you know the chances of making a mistake in interpreting Pune, Patna or Trivandrum is much lower than hearing P as B or D. So this is essentially the idea of introducing redundancy. You are giving more information than needed, and that helps you correct the error. Because even Pune, Patna and Trivandrum are going to be scrambled a little bit if the connection is not very good. But you are able to, in the context of this thing, it's much easier to interpret Pune very clearly, and then okay, they are talking about P. Right? So this redundancy, now when you come to digital communication, you can do various things, but the simplest, sort of most naive idea is to use something called a repetition code. This means that instead of, if I wanted to send only 1 0 to somebody, I will send 3 of them. Just extra copies. And the reason this works is that we assume that the noise channel is such that it's not going to destroy all of the zeros into ones and all of the ones into zeros. Just that sometimes, because of a fluctuation, a bigger noise, or a car passing by and honking, you heard the thing, right? So similarly, you assume here, there's an inherent assumption that your channel is not so bad, but it is bad enough that occasionally something like this would happen. And if that is the case, then it means that if you send 3 copies, most likely only one of them might get corrupted. So what you then do is you do something called a majority vote, So let's say I transmitted one as 3 copies of one, and then one of them changed into a 0. I basically look at all the 3 and I say, okay, most of it is 1, so this must be 2. So I then correct it and I say this is the actual result, so I'm going to interpret this sequence of digits as the binary digit. And same way for the 0 space. Now clearly this will not work if 2 errors happen, because then you will make the error inside. So this code is not very efficient in that sense. It will work only if the probability of error is very, very small. And this is the basic idea, but there are many, many more sophisticated ways to encode information. You might have heard about things like checksum and other things. I don't know, I guess we used to face these problems in our hard drives 20, 30 years ago, maybe not so much. But there are ways to do checks to verify that if the information which came to you is actually has been corrupted or not. And there are ways to even fix it by using these kind of ideas. One example of this is actually even Wi-Fi communication. You, as you move away from your router, the speed goes down. How do you make sense of that? The speed of light or the speed of microwaves is still the same. The amount of time it takes for things to communicate from one end to the other one is still the same. So why is it that when the signal gets weak, the data link speed becomes slow? It's because it has to now do many more operations of correction in order to recover a valid packet of data. So what's happening in a very crude sense is that data is sent and the other party says, sorry, that didn't make sense, and they will send us a message back and then it will be resent again. And hopefully after a few tries, you recover the correct information. And only then it will move forward. So the effective data translation rate goes down. You know, if we did not have error correction, classical error correction, none of this would work reliably. Cell phone communication, Wi-Fi, and then before that, DSL modem, where we just decided that we have phone lines everywhere. Why don't we try to send digital signals on it? It was not designed for that. But because of error correction, we could actually make it work. So the speeds were very low, because that is the maximum data rate. So this is sort of an idea of what it means to do error correction. Now we come to the quantum case. And remember, now the information you are trying to store is a qubit, the information that can be stored in a qubit. And the first problem you face, if you want to say that let me try the repetition type of code, is that this is not allowed. There's something called the quantum no cloning theorem, which says that if you have an unknown state, this is important, then there is no mechanism by which I can just create multiple copies. The unknown here is important because if I knew the state I was creating, I could apply the same protocol I used to create that state to create many more copies of the same state. But in general, you don't know what the state is. It's basically like saying I have a physical system, which is a qubit. I stored some information on it and I gave it to you. And I said, do whatever you want. You cannot do anything since you don't know what state I stored to make multiple copies. So there are some caveats that the true statement is that you cannot make a perfect copy, that you can make imperfect copies where the state will be close enough to the original state. But because you cannot do this, you cannot use the very simple idea which I just explained of just sending multiple copies in general. The other problem is that the errors which are possible on a quantum bit are not the same as the errors we just saw in the case of the classical bit. I made a big point that the only thing that can happen is 0 can be interpreted as a 1 and 1 can be interpreted as a 0. So that's the only thing that can happen. But that's not the case here. The states of a single qubit lie on a block scale. And what are we talking about as an error is that you started at some point, any deviation from that point, which is not being done by you in the sense of as part of the algorithm, is an error. Which means there is an infinite number of errors that is possible. This seems completely different than the classical case where there was only one possible type of error. So how do we even do or hope to do this? Right? And the third problem is that in classical case you can detect 0 and 1 and basically that's what it is, nothing changes. But in a quantum case, because in general you have an arbitrary superposition state, if I try to detect that state, it's going to collapse, as we learned in the first class, to 0 or 1, which means you actually destroyed the information you were trying to even retrieve or protect. So, given these three problems, it almost seems impossible, extending the ideas we just discussed, that it is even possible to do error correction in a quantum system. But it turns out magically that it is possible. And that's what we will discuss. And it's actually an extension of the repetition code, but thought about differently. What you do is you do take 3 qubits. So we are doing the same repetition idea. The first qubit is the one where the information is stored. That's where you are starting. The other 2 qubits are initially just in their 0 state. That's where they always start. The first term here is just the same state written in the 3 qubit basis. Remember I told you just have to multiply them together. So alpha is there, the first qubit is in 0, second qubit is in 0, third qubit in 0. So you have alpha 0, 0 and similarly beta 1, 0, 0. But this is just a product state. Remember from the first lecture, it's just another way of writing down the same fact which is given here, which is individual identities of each qubit. First qubit is alpha 0 plus beta 1, second qubit is 0 and third qubit is 0. Then you apply some operation which we call as this unitary operation of encoding, which changes this state into a state like this. It is alpha 0, 0, 0 plus beta 1, 1, 1. Now if we go back to this discussion on entanglement, remember that I told you this state gamma 0, 0 plus delta 1, 1 is an entangled state and cannot be created by just single qubit operations, which also tells you that here some kind of a multi-qubit operation is actually being carried out. This is actually just the extension of the 2 qubit example I gave you, going to 3 qubits, and you will see that in just a second. This state now, which is a 3 qubit state, has exactly the same information which is present in the original 1 qubit state because it has the same alpha and beta. Right? Essentially, alpha and beta is what is telling you what state that system is. But it is now stored as an entangled state of 3 different qubits. Each qubit individually does not store, has no identity in this picture, but there is an overall correlation between the different qubits. And this is actually key to being able to do this error correction. So how do we actually create this state? We actually use the same control NOT gate. So just to remind you, the control NOT flips the target qubit, which means 1 to 0 and 0 to 1, whenever the control is in 1, and it doesn't do anything if the control is in 0. So you start with 3 qubits. So remember now I'm showing you sort of this quantum circuit kind of picture. The first qubit is in this alpha 0 plus beta 1, the second qubit is 0, third qubit is 0. And this is the 3 qubit state. You then apply one control NOT between the first and the second qubit. And then you end up with alpha 0, 0. So just ignore the third qubit for a second. And you see that it's now alpha 0, 0 plus beta 1, 1. Which is exactly now an entangled state of the first and the second qubit. So it has now gone from a single qubit state to a 2 qubit state which encodes the same information. And all we have to do then is do it one more time between that same first qubit and the third qubit. And then you flip the third digit as well and you get alpha 0, 0 plus beta 1, 1. So this is just showing in practice how you would go from a situation of 3 separate qubits, you get the information stored on the first qubit, to 3 entangled qubits with the same information which is stored. Okay. So this is just an extension of what we do. So we are now in this state, and basically I'm going to explain now that this state allows you to correct a specific type of error. And that error, again we are going to basically say, it's a simple model, it does not represent the true situation in most cases, but it serves to explain why something like this actually works. So in order to detect an error, we have to measure some other quantity which tells that the error has happened. Because if you try to measure the state, then it will collapse, and we don't want to do that. So these states are now called 0 logical and 1 logical. So 0 logical is 0, 0, 0, and 1 logical is 1, 1, 1. And then any superposition of that is now your new state, which is composed of many physical qubits. So there is this terminology that the physical qubits are the actual physical individual qubits, and the logical qubit is an effective qubit created from all of these physical qubits. Now we'll start to look at what are the possible errors that can happen. So again, the errors I'm allowing is that the 0 on the first qubit could become 1. I told you in the beginning that that is not the general case, but there will be. I'm allowing the errors to be of the type where 0 goes to 1 and 1 goes to 0. Now, when the system is in an entangled state like this, these are the only possibilities that can happen. Which means the first qubit has flipped, so this 0 has become 1 and that 1 has become 0. Remember, you have to update every part of the superposition using the same rules. So this, for example, could have been done intentionally by applying a NOT gate only on the first qubit. So we are basically saying that the environment noise is doing an accidental NOT gate on the first qubit. That's the error. It can happen randomly, but that's what we are allowed. Similarly, you can do that for the second qubit or for the third qubit. See, all of these are also still entangled states, just of a different type. So in the first case, the first qubit has flipped. In the second case, the second qubit has flipped. And in the third case, the third qubit has flipped. So these are the only 4 options that exist under this error model. So either no error has happened, or you are in this state, or you are in this state, and you are in this state. So the job of the error correction protocol now is to figure out which of these is true without learning anything about the alphas and the betas, without projecting the state into this. This is called, this kind of a measurement is called a parity measurement. Because essentially you are looking at pairs of qubit and asking the question, are they the same or are they different? So different here just means they can be 0, 1 and 1, 0. Same means they have to be 0, 0 or 1, 1. Now we look at that from pairwise, which means the first and the second qubit and the second and the third qubit. That's what this symbol means, 1, 2 and 2. So in this case, the first 2 qubits are always the same, and the second 2 qubits are also always the same. Mean they are both 0 or both 1. So this is called even parity, and both of them are even. In this case, the first pair is odd because it's 1, 0, 0, 1, and the second pair is 0, 0 and 1, 1. So that is even. Similarly, this one is odd, odd, and this one is even odd. So if we could detect the parity of pairs of qubits, it actually does not tell us anything about what the original state is. Like it doesn't even depend on alphas and betas. And now you have 4 different options, and depending on which of these options you end up with tells you whether no error has happened. And remember, no error has happened because it's a probabilistic process. Whenever you are doing this, it might not have experienced an error. It's again, we are doing the error probabilities are small. Or the error has happened on the first qubit, or the error has happened on the second qubit, or the error has happened. Once you know this, you know how to fix it. Because remember, the environment did a random NOT gate on one of the qubits. You just have to do the NOT gate again. Now intentionally. But you need to know which qubit to apply the NOT gate to. And that's what this information tells you. If you are in the first possibility, you don't have to do anything. No error has happened, so you just let it be. If it's the second possibility, you know that the first qubit is flipped, so you apply a NOT gate and it goes back to this state. Here you apply a NOT gate on the second qubit, and you go back to the state first. And same way for this. Now in practice, how do you do this parity measurement? The point here is that these measurements reveal an orthogonal quantity to the state which is stored. And this is possible because now you have a bigger phase space in which these states are existing. Remember that you only needed 1 qubit to actually store that, but you have now pushed this qubit into a bigger space of 3 qubits. And there are many other possibilities which allows you to detect some property. And here that some property is the parity, which is telling you the information of which qubit has experienced the error. And when you do that, you actually don't reveal any information about the alpha and the beta, in the sense that if I repeat that experiment, I'm not going to be able to construct a probability distribution which will depend on alpha square and beta square. That's what it means. So, because it does not reveal any information of that, your information is safe. All that has happened is that we have fixed the error and put it back into the state it was. So, error correction involves always two steps: checking for the error and then correcting for the error. So it's a feedback process. So it's not like a passive thing. It's something you actually do. So remember, all of these things are operations, right? The first, even the encoding is an operation, figuring out the parity is a measurement, and then the correction is an operation. So it's actually a small algorithm which you are running, which ensures that your state always remains in this particular configuration, which is the error-free configuration. So it doesn't mean that the system is never without error. It will have errors, but you will be able to correct it. And you have to do it fast enough so that multiple errors don't accumulate. So same way this protocol will not correct it if more than one qubits underwent a flip, because then this simple scheme will not work. So again, the assumption is that on the time scale at which you are doing the error correction, which means you have to choose that every 1 microsecond I am going to run this small algorithm and restore the state. If for some reason during that 1 microsecond time window 2 errors happen, then you are dead. Basically, you cannot do it. But that's sort of a practical assumption. Now, in practice, how exactly are these measurements done? They are done because how do you even make a measurement which allows you to detect the parity? And for that, this is maybe slightly complicated, and you can note this part. But essentially, we use additional qubits, which are called ancillary bits. So 2 additional qubits. These were the 3 original qubits. And then you do a C0 gate between the 2 qubits you are interested in measuring the parity of. And you do it like this. And similarly for the other 2 qubits. And then when you measure the ancillary qubits, so they get projected and you will get a 0 or a 1. But when they get projected, because they are entangled with these pairs of qubits, it actually projects the entire system, the 3-qubit system, into one of these different subspaces. So for maybe the third year students who have studied some quantum mechanics, you can try to work this out. It's actually very straightforward to write down what the state is, and then when you know that if you reveal this information, because this is entangled with this one, you know that if this one is 0, then these other 2s will end up in 0 or 0, 1 or 1, 0 or 1, because of the entanglement. Because you remember that the moment one of the pairs of the entanglement is revealed, all the others are immediately projected. So that's what is happening. So this sequence, this is now also a small algorithm. What its job is to figure out the parity and encode it into the state of one of these 2 qubits. So these 2 qubits now reveal 4 possibilities: 0, 0, 0, 1, 1, 0 or 1, 1. And those 4 possibilities correspond to these 4 possibilities. So you see that error correction involves an overhead. You have to run a small algorithm, do some measurements, look at the result of that, and then decide whether to correct it or not. So this is where also the problem lies, that if your system don't have low enough errors, the overhead of doing that algorithm could introduce more errors, and then you will actually not recover. I will comment on that towards the end once more when I show you some very recent results from the field. So that's basically what is doing. This was an example of only one type of error, and as I explained earlier, there are actually infinite number of errors. But it turns out that you can break this up into a few elementary types. So the first error we talk about is a bit flip, where 0 goes to 1 and 1 goes to 0. You can also talk about another error which is called a phase flip. So this is an error when something which is pointing on the equator along this direction gets flipped to point in exactly the opposite. So remember, again, these are artificial cases we are creating, but it turns out that you can break up all the errors into these elementary errors. And the way you correct for this kind of an error is using exactly the same method, but you introduce this Hadamard gate in the beginning, which remember created a superposition from the ground state. And what that effectively does is that it flips the phase flip axis into this axis and turns it into a bit flip error. So you convert the phase flip error into a bit flip error and you recover it in exactly the same way. So you do the same thing after that. So you just need a few extra gates to correct for the phase flip. But still it seems like I've only chosen 2 examples. The magic really happens is, so here after correction we put the Hadamard back to reverse it. The magic of error correction is really the fact that when you do these measurements, even if the errors are not of this type, this type where 0 goes to 1 and 1 goes to 0, or the equator pointing this way goes to the equator pointing that way, it could be anything. It could be a state which is here and it has gone slightly over there. When you carry out these so-called parity measurements, it actually collapses the system into one of these possibilities. So the magic here is that the parity measurements converts the infinite possible errors into a finite set of correctable errors. The main difference is that these errors you know. So it's actually very strange. Sometimes the actual error, in the sense that the original state and the error state might be very close to each other, but you have no way of knowing it. But the process of error correction can actually amplify that error and make it much worse than it was. But you know what it is, so you can fix it. So this is the reason why this works. And then, so these examples I showed you of bit flip and phase flip, they are also invented by the scientist Peter Shor, some of you might have heard. And combining these, he created a code which consists of 9 qubits, which allows you to correct any type of error. Later on, people figured out more clever ways of doing the encoding, and it turns out that you don't need 9 qubits. There's something called Steele's 7-qubit code. And there are also other codes where the number of qubits itself, which is needed for error correction. So what that means is that how many physical qubits per logical qubit is not a fixed number. It changes depending on how much error you have. If you have more errors, then you need more number of qubits. If you have less errors, you need less number. That's very technical, but I just want to mention, because surface code is something which is considered the most practical way of implementing error correction in today's architecture. So that's basically the story of error correction, and you now see hopefully that it is actually possible to preserve a quantum state. There are many more complicated things here. This is just about storage. Now you have to think that, okay, I have to do gates between logical qubits in order to run an algorithm, and you have to do that while you are still error corrected. So there's a whole bunch of stuff beyond this, but all of this has been worked out theoretically, and it's possible in principle. We haven't done those kind of operations just yet, but this is going to be very, very crucial. So we'll now move on to some examples of algorithms. So this is the Grover's search algorithm. The problem is to find a particular card, say the 7 of hearts, in a deck of cards, some sample of not full cards. This is called searching in an unsorted database. Now, how do you do this in practice? The only way you just keep opening the card one at a time, and at some point you will land on the right card. So you could get lucky and get the card with the first try, or you could be extremely unlucky and get the card in the last try. If you average it over all possibilities, then basically on an average, you have to at least go through half the number of cards out of the size of your database to find the correct one. So which means that as the number of cards grow, the number of steps needed or the time needed to find the correct one also grows linearly with the number of the size of the problem. What Love Grover showed that there is a quantum version of this problem where you can do better. So what's the quantum version of this problem? Instead of some different elements, you are now saying that I have different basis states of some n qubit system. Okay? What does it mean? Let's say 3 qubits, you can go from 0, 0, 0 all the way to 1, 1, 1. There are 8 basis states. And one of the basis states is the special one. That's the one you're looking for. And there is a particular operation which we call as the oracle or the black box. And what that does is that if you send in a state, which is a superposition of these basis states, then it just changes the sign. It puts an extra negative sign on that special state. So this is the redefinition of this problem in the quantum picture. And your job is to find out which special state, which one is the special state. So you are given these blocks, all you know is that there is one special state and this particular operation. So this is basically a unitary operation. You don't know what's inside. This is a black box to you. And all you know is that it does this particular operation for that special state. And again the problem statement is how many tries, how many evolutions of this thing is needed before you find the correct state. So what Love Grover did was figure out a quantum algorithm to do this. And again, this is an example of a problem which is difficult to find, but it's easy to verify. Once you have found it, it's easy to check that is this what is really happening. And what he showed is that he can create an algorithm where instead of the problem going linearly with the number of size of the elements here, it goes as square root of 1. And I have plotted n versus square root of n, so you see that for very large numbers there is a huge benefit. The number of steps required will be smaller and smaller relatively speaking. So it has a practical advantage of doing this. So how does this actually work? So let's take now this 3-qubit example. So there are these 8 basis states and we have 5 as the special smart state. And this oracle will return this when this is not 1, 0, 0 and it will return minus of x when x is 1. So this is just a matrix which does that. You can ignore that. It's convenient to look at this in sort of a vector picture. And the idea here is that you define one vector as the special state, which is the mark state here, and you define the other vector as a superposition of all the other states. You're just breaking this up and coming with a way to visualize this kind of a state. Then the total state at any point of time is basically just the sum of these two things. So it's sort of the sum of this, a vector sum of this one and this bigger, more complicated vector. So you can write it like this. So the full state is this special state in combination with this. So I can write it as a vector here in this two vector space, 2D space here, with one axis being W, which is the special state, and the other one being S. So what are these coefficients? These coefficients are the coefficients in front of the wave function of that particular term. So it gives you the weight or the probability of that particular state. Okay, so this part is clear. This is all we have done is just taken the same state and broken it up into 2 parts. One part which is proportional to the special state, and the other part which is the rest of the stuff. So it has to be some combination of these two only, because that then covers the full 8 basis states. So if omega w becomes minus w, that just flips the sign of this thing. So you start the search problem by creating your input state as an equal superposition state, which means all the weights are equal. So this particular example is a very good example of why the ability to have a superposition state gives you an advantage. So you start with an equal superposition state that is represented like this. Then you send it through the oracle. This is the box which is going to do that inversion. And what that box is going to do is going to change the sign of the W, which was pointing this way, into a negative one. So it's going to now point in the opposite direction, which means the net resultant vector has gone from pointing from here and to this way. So remember, the net resultant vector is the current state of your 3-qubit system. That's how the system is evolving. So it was initially pointing this way. Now after going through the oracle, it points in the other direction. Okay. So if I write now the weights of all of these elements of this wave function, basically what has happened is that that particular wave function amplitude has been made. This is just two ways of looking at the state. Then comes the main part, which is the something called the inversion of this step. Sorry, that's the first step. Now we have the reflection using what's called the diffuser. That's a term. But what that does is that it reflects the state around the original state. The part I'm not going to explain is that how exactly it happens, but there is a unitary operation which carries out this process, and it does not depend on what the state is, but it does basically flip it. So it basically is reflecting about this axis. So what had gone from here to here now goes from here to here. Now what has happened, the net result of this is that this total vector, which is the current status of your 3-qubit system, is pointing closer to W. What does that mean in terms of the probabilities of all the individual basis states? The probability of this new state is higher for the special state, and all the other probabilities have become lower. So in this picture, initially all the amplitudes were identical, which was the equal superposition state. Then we had a negative thing, but the negative one probability is square of that. It's still the same. But after this operation, this special state's amplitude has increased because it has now gone closer in this way. And correspondingly, all the other amplitudes have to come down. Right? And you just have to repeat this process now. So this is now your current state. You send it to the oracle again, this becomes negative. Then you do the diffuser, and then this becomes again improved. So as you repeat this process, the special state's probability or the amplitude will keep growing, and all the other probabilities will come down. So this is a classic example of the generic picture I showed you in the first lecture of what a quantum algorithm does. It's essentially increasing the probability of the right answer and decreasing the probability of the wrong answer. And remember, the answer lies in the measurement of one of these particular states. So you do this, and what Glover proved, that you need approximately square root of n, where n here is 8 in this problem, to converge to a situation where this state will have unity or very close to unity amplitude, and all the other probabilities will be 0. And this is also an example that depending on n and the accuracy with which you do it, you might not get exactly unit amplitude and exactly 0 for all the other ones, but you just have to repeat it one more times, and because the probability is high enough, you will measure. So what happens at the end of the algorithm? You look at the state of that quantum system, and because there is only one wave function surviving, you will get that particular answer, in which case it was 1, 0, 0. So then the final measurement tells you what the special state is. And it only took you square root of n iterations of using the oracle, as opposed to the classical case. So this is a very good example of how a superposition, the fact that you started with all of these possibilities and then converged into the right possibility. So then there are many more, so we'll just go through some of these what they do. I'm not going to explain the algorithm. Shor's algorithm is basically something that was invented to find out, solve the prime factoring problem. So these two are prime numbers. Multiplication is easy. Mathematically, the reverse problem is very hard. This is too small a number, you can solve this in mathematics in no time. But as the number of these digits become larger and larger, the reverse problem becomes exponentially harder. And this is actually the basis of encryption called RSA encryption. All our data on the internet, on ATM transactions, everything uses RSA encryption and relies on the fact that only the person who knows the two individual numbers can decode the information, but this number is known to everybody. So if you are an adversary, you need to crack this problem, and that's essentially impossible even in the most powerful computers available in the world. That's what guarantees the security, and this is something called a public key encryption system. But Shor showed, using his algorithm, that his problem no longer, in the quantum version of this problem, the complexity or the time does not go exponentially, but only polynomial. So you can get estimates like something that might take 10 to the 24 years can now be calculated in 20 seconds. So a lot of people are worried about this because once a powerful enough quantum computer comes, none of the data which we transact is going to be secure. Don't worry, such a machine doesn't exist as of today to the best of our knowledge and is unlikely to exist for the foreseeable future. And there are already alternatives being developed. This is serious in the sense that people are already working on other types of classical encryption methods which cannot be broken by a quantum computer as well. And also there are now new methods of encrypting information using the laws of quantum physics as well. There's something called quantum key distribution, where the guarantee doesn't come from the complexity of the problem, it comes from the laws of quantum physics. So those cannot be broken. And those systems are actually almost commercial. And even in India, there are now a few places where they have created test things, especially the defense and the military is very interested in these kind of things. But just a side fact, which I myself was only made aware of about a year back, is that people are still worried because today data storage is cheap. And the point they're making is that I can store all these secret communications I'm intercepting, keep it with me for the next 20, 30 years, when a quantum computer will be invented, and then I will be able to decode that data. And there are certain types of information which you would like to preserve, or a country or a defense would like to preserve for the foreseeable future, maybe 50 years or 100 years. Right? Who killed John F. Kennedy? Or for that matter, in the Indian context, Lal Bahadur Shastri. So this is something people are worrying about, and I was very surprised when I heard about this, but I said, yeah, okay. There's a very nice YouTube video which you can check out where Shore himself tells you, he's a really interesting character, he tells you how he sort of invented this algorithm and what is going on. Like that. So if you're interested in sort of history of things, this is a nice video. So moving on, I had made this point earlier that one of the applications which actually scientists, like physicists and things are really interested in is simulations. And this is essentially because doing quantum mechanics on classical computers is difficult. And it's very simple to see, it's because of this exponential scaling. As if you consider a quantum mechanical problem as something being represented by n qubits, then as the number of qubits grows with the size of the problem, the number of things you have to keep track of grows exponentially. And soon you run out of space and processing power and you just cannot do it. This is basically doing quantum mechanics by writing down the Schrodinger equation on a classical computer and solving it, which is perfectly fine. For a small number of qubits, it works perfectly, in fact works better than today's quantum computers, because that will not make any error. And Feynman had recognized it back in the 80s, where he said that look, nature isn't classical, so if you want a good simulation of it, you should use quantum mechanical elements to simulate. So the basic idea is that you're trying to mimic the behavior of one quantum system which is of interest to you, maybe some chemical or some material you're trying to analyze, but you cannot directly play with it or analyze its properties in a sort of to really know the quantum mechanical properties of it. But you have another system which you put together in such a way that it can mimic the system you're trying to study, but because this is controllable, you can probe it, you can measure it, you can truly understand it. That's why it's called a simulation. And there are two ways, broad ways of doing this. One is called a digital quantum simulation, which is essentially writing a quantum algorithm which can run on a universal quantum computer like the one we have been discussing. The other is a very problem-specific model. So, this is equivalent to saying that I don't know, you guys probably, but the teachers here know, back in the day there used to be a separate word processing machine, right? It was meant only for doing word processing and did nothing else. So that's a specialized machine for a particular task, but today's PCs can do word processing, can play games, can solve equations, so that's a general purpose and that flexibility comes from the program. So similarly, a universal quantum computer can run an algorithm which can implement a quantum simulation, or you can build a specific quantum hardware which is simulated, it's going to simulate only a particular type of problem. So both of these things are being, and that is also sometimes called analog quantum simulation. So they will have less focused, like a narrow focus of application, but they can maybe work more efficiently. And it's likely that useful analog simulators will come before full digital simulators because you have to build a full quantum. So some examples basic things people have done so far. These are really toy problems. It's like finding the lowest energy state of small molecules like the hydrogen atom. This can be solved analytically and trivially on a computer. But what they are showing here is that there is a way to map this problem onto a certain number of qubits. In this case, this was mapped onto a 4-qubit problem. And they were able to basically get this curve, which is energy as a function of interatomic distance, so that you can find the lowest energy and say, okay, that's going to be the bond length of this particular molecule. And the dots here are basically data which are created from this quantum computer, and the line is the analytical solution. So you see this sort of match, and they actually have to do some kind of what they call error mitigation to improve it and make the results match better. As you go to a larger molecule like the lithium hydride, then it becomes a little bit worse, but then they are able to make it match better. This is not an application you can sell today, right? This is trivial. But it's a proof of principle that these kind of ideas. And there are many other things. People have also studied photosynthesis, by modeling that problem on a quantum system, because there is this belief that one essential part of the photosynthesis process is the quantum mechanical process. And they basically made something where they scaled down the problem by a factor of 10 to the 5, and they studied the role of environmental noise in this problem. This was again, both of these examples were actually run on superconducting quantum processes, and they actually showed, sort of counterintuitively, that in this case, the environmental noise actually helps the efficiency of the photosynthesis process. Generally, we consider noise as doing a bad thing, but in this case, they are actually able to show that sort of match with what people have observed in the real system. So there are many other things one can do. Essentially, if you really let your imagination run wild, and in my case, it's basically like you don't have to go to a chemistry lab. You can do all your chemistry on your computer and nothing will explode and smells. I don't know, I hope there are no chemistry issues. But essentially, any quantum mechanical reaction or something that you can do in real, now you can do it. And this actually has a huge cost benefit, if you imagine. You don't have to try this, you don't have to do risky reactions because nothing is going to explode. There might be a message which says explosion occurred, but that's about it, right? If you think about it. So that's really the possibility, because you can now model all quantum mechanical equations with a lot of detail. Of course, I'm still talking about things which are way in the future. When you go to many systems and complicated systems involving many chemicals and fluids and other things, it's not going to be so easy to write the algorithm or build a simulator for that. But it's potentially a possibility. People are looking at protein folding problems using quantum mechanical algorithms. And there are also applications in high energy physics simulations as well, because they're also quantum mechanics. On the other hand, there are also problems in optimization, things like the traveling station problem. There are applications in finance people are looking at. And the real thing is that there is really a lot to be discovered, but it's very challenging because apart from maybe some of these where we know how to go about it, clear algorithms for doing the other things don't exist. Because it's extremely counterintuitive to know how to use these principles of superposition and entanglement for a particular problem and whether it will even benefit. It is not true at all that all computation problems will run better on a quantum computer. That's not true. Most of them will not. Only special problems with special characters and symmetries. But people are hoping that there is a whole lot more to be discovered, apart from the ones we sort of already know. Okay. So to finish off quickly in terms of where we are or where the world is, there are some important landmarks which have taken place in the last 2 years. This one you have probably heard. This was the result from Google, where basically it's the first claim for performing a computation significantly faster than the best classical version. The best classical version is using one of the most powerful supercomputers available on Earth, and they made an estimate that the calculation which their quantum computer using 53 qubits did in 200 seconds would have taken 10,000 years on the supercomputer. Obviously, they did not run it for 10,000 years on the supercomputer. It's an extrapolation of that system. But the particular problem, which is actually called the sampling the output of a pseudo-random quantum circuit, is a completely useless problem in the sense that it has no application. It's just some quantum mechanical problem And we just compared it because we wanted to reach to a stage where we want to say that there are things which a quantum computer will be able to compute, which a classical computer will not be able to compute. So soon after that, so this was with superconducting qubits. Soon after that, a similar problem was done on a photonic quantum processor. This was from China, and there they showed that the factor was even larger. It was 200 seconds versus 2.5 billion years. And it's a similar type of problem, again useless as of now, and but it shows that a quantum system can be much powerful. And then a couple of years later, things got pushed further. A Chinese group did an experiment with slightly more number of qubits. Remember, the things grow exponentially with the number of qubits. Each time you add 1 qubit, everything doubles. So even 3 qubits is actually a significant number. And here they did a more realistic comparison. They said that it's what their circuit took 1.2 hours. Supercomputer would have taken 8 years. The previous result by IBM was quite controversial. A lot of people say that their analysis is not exactly accurate. And very recently there was a paper which said that they compared it, assuming that their quantum computer was actually perfect, but their quantum computer was very noisy. So if you try to simulate a noisy quantum computer, you can actually do it with faster and with less resources. So this is still, these are all the way, in fact, somebody said, and I like that comparison, is that you should really think of them as experiments of the type of the Bell's inequality test. They started 3 decades ago where there are some loopholes and then they were improved and then they were improved. So over the next, few years to decades, we will have many more of these experiments. Most of them might be useless in terms of applications, but they will keep demonstrating that the quantum computers are working the way they are supposed to. And there was another one using a bigger quantum processor. So this was the result I was mentioning, and this is actually like just a few weeks old. And this is about error correction. Okay. 2 groups. The first one here is from the Yale group. This is the group I did my PhD work in. And then a group from China. They both demonstrated for the first time that an error-corrected logical qubit lives longer, has higher coherence than the best qubit in the collection of qubits. So this particular type of thing also uses superconducting circuits, but it doesn't use the Josephson junction-based nonlinear oscillator as a qubit. It actually uses the linear cavity. In fact, these are machined cavities. These are like chunks of aluminum which have been machined high purity aluminum so that their losses are as small as possible. And they use a different encoding speed. Unlike the ground state and the excited state, they actually use superpositions of coherent states. Maybe if it's jargon, don't worry about it. It's a different method which actually lends itself naturally to do error correction. So these parity measurements are very easy to do, and they're able to show. And maybe just for comparison, I can look at this curve. So this curve is sort of, just imagine this as the relaxation decay curve. It's not exactly the same. It's some people process what they're doing. But this is the Josephson junction system which is in there, which is decaying with a time constant of 91 microseconds. This is the cavity, the high coherence cavity, which is decaying with a time constant of 274 microseconds. And then they do error correction on the, this is the uncorrected binomial code, and then they show that here you have a slight improvement between the actual code and the error corrected code. And that improvement is about 16% in this case, and it's about a factor of 2 in this particular case. This is a huge milestone because finally we have shown that error correction actually makes things better. And this comes back to the fact of the overhead. Because error correction itself involves running some code. If your code is too lengthy, then you introduce more errors while you are running the code itself. So this involved clever encoding, improvement in the coherence times, all of that come together. So this is a major thing, but it's happening in an architecture where it's not clear how we will make multiple qubits just yet. So there are proposals. So I'll just take 2 more minutes to quickly flash some of the things which are happening in our group. We have been working on this idea of multimodal quantum circuits. So one of the first things we did was invented this 3-qubit circuit. It's basically an oscillator which can oscillate in 3 different ways. So it has 3 normal modes, and each of those normal modes can be treated as a qubit. But because it's part of the same physical system, so this is what the device looks like. And there are 4 Josephson junctions instead of 1. And because they are all part of the same, they are actually coupled. So it creates an effective 3 cubic Hilbert space, which is much easier to manipulate than putting 3 separate qubits together in the conventional way. And we showed that we can run some algorithms better than what the standard architecture allowed. We also work on ultra-low noise amplifiers, which are very crucial for detecting these very tiny signals which are used for measurement. A derivation of this multimodal 3-qubit circuit gives rise to another single qubit circuit where we are able to do better measurement, like the ability to resolve the states is better. This is actually ongoing work. And then this is something we did some our first results from a couple of years ago. We created a method for coupling qubits by putting it around a circle, around a piece of transmission line like this. So there are all qubits sitting here, in such a way that even though they are on a circular circumference, these lines tell you the qubits with which they can interact. So remember I had made this point about a 2D layout of qubits and only nearest neighbors can interact. Here this qubit, which is not all the way on the other side, actually interacts the strongest. And the way this works is that this circular path allows, it's like a waveguide, it allows signals to go from one qubit to another qubit via both clockwise and anti-clockwise direction. And then depending on the path lengths it traverses, it will provide a constructive or a destructive interference, and that's what sets up this. So by carefully choosing the spacing of these qubits and the frequencies at which they operate, we are able to show that in a 12 qubit network, which is spaced with 30 degree spacing, every qubit is connected to 9 other qubits and is not connected to 2 qubits because of complete destructive interference. And also in such a way that the coupling strengths are relatively uniform. Otherwise, you can do many other ways where the coupling strengths could be all over the place. So that had to be figured out. So we are now working on using these kind of systems to do further experiments. This is a sort of a technology demonstration project we are doing in collaboration with DRDO and TCS, Tata Consultancy Services. And this, if we do it in time, this should be India's first quantum computer ever built. It's a very modest 7 qubit system. It uses an unusual architecture. This is actually a prototype of the processor. You can see it's an aluminum box, which is about 7 centimeters on this size, as opposed to the tiny chips I showed you. And this is basically using the strengths we have and the limitations we have in terms of what we can and cannot do in our labs. And these red arrows actually show where the individual qubits will be placed. So it's not actually like a 7 qubit chip, but it's a structure into which 7 qubits can be placed individually. So this allows us to choose the best 7 qubits we have and we can put them, as opposed to creating a single chip if we currently don't have the resources to do it. So this will be put together fully. We are currently testing a 4 qubit system, and this is how they are going to be connected because of the way they are laid out on this real structure. So this tells you which qubits they can interact with. So we have chosen this deliberately to minimize the connectivity for those qubits. Because that introduces some kinds of errors. So as part of this project, we are also developing some custom electronics that's been done by the Vijayaraghavan colleagues. And TCS is developing the web interface, like those who have worked with the IBM system. So we will now have a web interface which will then allow all of you to access this quantum computer once it comes on. Hopefully it will work. The target is somewhat towards the end of this. Okay. So essentially, that's what I have to say here. We looked at quantum algorithms, saw how superposition plays a role in the Rose algorithm, how entanglement plays a role in the error correction, and we saw example of how to do error corrections. And then I discussed something about quantum simulations and talked about the current space. The future is basically that we have to solve the error correction problem for a practical settings. We have to figure out how to make the electronics more compact and simpler so that we can control thousands of qubits and we don't need like a building full of equipment. We'll have to make advances in cryogenic technology to be able to come back. This is of course very specific to superconducting qubits. There are similar milestones which are needed for every architecture has its own problems which has to be solved. I wanted to particularly thank Sumeru, who graduated from our group a couple of years ago, and Dr. Malvi Chand for helping many of the slides for all of you. So Thank you, and I will take questions.
Thank you for the session. Now I would like to ask faculty and the students to ask questions from previous talk and
Yes.
So I have actually two questions from yesterday's talk. So yesterday you mentioned superconducting qubits basically. So I was thinking like in superconductors we usually have these Cooper pairs, right, which are bound already. So yesterday also showed transmitters also which are in a graph yesterday in the last slide. So does these Cooper pairs, can they actually be used as qubits because they are already bound and they are stable, or will they affect, like if we like the oscillatory system that we are building, the Josephson?
So your first question is that can we use Cooper pairs as qubits?
Yeah, because they are already cold and bound, right? Those electron pairs.
Well, so the thing is, you don't have access to an individual Cooper pair
yeah, okay.
so easily in any system. And then you have to think about what are the states of that kind of a system. So first of all, having an isolated Cooper pair has no meaning. Remember, I mean, I don't know how much superconductivity you have been exposed to. You have seen pictures of Cooper pairs showing two electrons in the circle around you. You know, just like the picture of the electron going around a nucleus in a circle is incorrect, these electrons need not be next to each other, right? It's a depiction of an effective coupling between electrons with different momentum states, which happens because of interactions with the lattice itself. So the idea of an isolated Cooper pair has no meaning in this context. Now, how the Cooper pairs affect the oscillatory properties? It does not. The underlying point is that if that metal, let's say that aluminum, the same structure, was above the transition temperature, then the transport is happening through normal electrons, which are unpaired electrons, and they will give rise to dissipation. Because we are in the superconducting state, the currents which are flowing in the inductors and the capacitors, they are composed of the superconducting paired, the Cooper pairs. So they then transport, move around without inducing any dissipation. So if you break Cooper pairs, for example by elevating the temperature slightly, or as I was mentioning, from high frequency radiation which can come into your system if you have not shielded the system properly, then in your bath of what we call as the superfluid, or in this case, there will be some pairs of electrons which will be broken. So then you will have a majority of transport which is dissipationless and some which will induce dissipation. And this is important to keep in mind that this is AC transport. See, if this was DC transport, the superconducting path will short circuit the normal path. So imagine two wires, right? You have a resistor and you have another resistor with zero resistance. If I measure the total resistance, it will give you zero. So a DC current will always flow through the path of the lowest, but when you have an AC current, that short circuit is actually like an inductor. So it will have some inductance. So there will be some AC current which will flow through the inductive path and some which will go through the resistive path, and you will always get dissipation. So that's why even a very small fraction of unpaired electrons can be detrimental in terms of inducing losses.
So one more question I had from today's talk. So again, in quantum error correction that you mentioned, so we took 3 qubits and their entangled states, right? So we have these pairs 0, 0, 0, 0 or 0, 1, 0, 1. So but this is only for like 3 qubits, right? So obviously when we increase the number of qubits, let's say 4, 5, 6, the number of pairs that we have to go through will be higher in every time, right? Because we have to select. So is there any efficient way of doing it, or like do we have to do this parity operation?
So I think you are mixing two different ideas here.
Okay.
The 3 qubits were chosen for a particular error model.
Oh.
Right? Those 3 qubits represent one effective qubit, and they only correct the bit flip errors, which is the error of time which takes 0 to 1 and 1 to 0. I also mentioned the phase flip errors, which can be kind of transformed into a bit flip error and corrected. But if I want a single system to correct both bit flip and bit escape, Shor invented the 9-qubit algorithm. So that includes 9 qubit. It doesn't mean it's a 9-qubit processor. It's actually a 1-qubit processor.
Okay.
Because those 9 qubits together are representing one logical qubit. And the number of parity measurements needed to correct both bit flip and bit flip is obviously more than 2. But then there is something called the scheme code which uses 7 qubits and it requires a certain number of parity operations. But all of that is still one logical qubit. So as you now try to build a processor which is made of error-corrected qubits, then you have to think in multiples of these things. So if you're using Shor's code, then for each effective qubit you will need 9 physical qubits. In the surface code, which I didn't discuss, it's the way it works out is that you can have hundreds of qubits representing one effective qubit. It really depends on the amount of error you have. The smaller the error, the less number of qubits you need, but it's flexible. So what people are thinking that it also only requires nearest neighbor interaction. So in a planar architecture, this is very, very easy to implement. Whereas nobody is actually implemented, to the best of my knowledge, the 9-qubit Shor's code or the 7-qubit scheme code, because the connectivity you require to do all the encoding and the decoding operations will require so many operations in today's processors that you will just not be able to error correct. So that's why people are looking at the error correction protocols which can tolerate larger errors, because our qubits are quite error prone. But maybe tomorrow somebody will invent a new one. This last example of using coherent states to store has a very small overhead on the error correction because of the way the qubit architecture is constructed.
Thank you.
Okay? Yeah.
I might be wrong here, but you said about cloning sugar, right? So, for example, you can't clone an animal. So, for example, in a classical bit system, we know that suppose the speed is 0, right? So, for example, in this case, wouldn't you just know what the actual state is when you are transmitting it?
Not always. So, the idea is that if it's a very simple example of the transmission problem I gave you, and I am the one who is generating the information, then yes, I can just make lots of copies. So the idea of a general quantum memory which preserves any state, and the method for preserving any state should be not dependent on what state. You cannot have a different protocol for every type. The most general case is that there is an unknown state. How to make sure that that state is preserved. So the error correction basically allows you to do that because all the protocols don't depend on what the coefficient is in front of those states. They only depend on these parity measurements. So for the simplest example which you mentioned, yes, if I am the one generating the information, I can send as many copies of those I want to send. But if you imagine that you want a quantum memory inside a quantum computer, temporarily store a result. So what does it mean? You had some qubits, some unitary operations were run on it, and the state evolved to some new state. You have to do, as part of the computation, run some other algorithm on a different set of qubits, and then do something finally with those two states. So what do? You have to mark that state somewhere. But you cannot predict in every case what that state is. So quantum memory, which is error corrected, should be independent of the logical. What you are saying for that specific number.
Can't we just do, for example, what the result is? And you know that initial state, if you just run it through, you know that when you can create another state to do the calculation.
No, but it doesn't work for the most generic case, which means that you have to work out how will you calculate the final state of the operation. That itself is a problem. If you have to do it on a classical computer, as the number of qubits increase, the overhead will be large. Maybe I'll give another example. If you're imagining that I just run parallel computation, the same initial state, I'll just run many of them, and at least one of them will give you the correct answer. How will you know which one? If the errors are happening randomly, you don't know which one will happen. So it doesn't. Yes.
So we were talking about the transformation in using unitary gates in single qubit systems. My question was in classical systems, right? By the convention, we could observe and we could talk about the principle of least action. So whatever time invariance happens in quantum system in Hilbert space, right? It happens before measurement. So is it possible that we could actually derive a relation between the random probability of the solution that we are taking and the path it would take during this operator per se? So if we could do that, I mean, could we in theory apply the measurement operator and the unity operator at the same time in the qubit, thereby reducing any neglecting chances of error by actually understanding the movement through the plot space?
So you want to apply the unitary operator and the measurement operator at the same time, but for what purpose?
So
I mean, you can.
yeah. So the problem what I am trying to bring to is, like for example, we talk in very simple terms. Let's say my qubit uses an X gate to switch from 0 to 1 state, right? So what I'm trying to figure out that would there a path that it takes or
Oh, I see.
Yeah.
You're asking, can one use the measurement
yeah,
to create a deterministic
right,
operation?
right.
Yes and no. In fact, people have done experiments of this type. The measurement is always going to induce a random evolution on the cube.
Right, but
Okay. I was talking about weak measurements with somebody yesterday. I didn't get it with you. So let's start with standard projective measurements. Okay? You're initially in a equal superposition state. You apply the measurement and you randomly end up in 0 or 1. You can call that as a state transformation if you like, but it's random. There is something called a weak measurement, which is sort of an incomplete measurement. And one can show that this process is actually continuous. Which means that if I take many incomplete measurements, that together gives a complete measurement. So at the end of that several incomplete measurements, you still have the same result that you will end up in 0 or 1 randomly. But the path it takes is actually a continuous path on the surface of the block sphere, and it will be like a random walk. Now, if you want to use this to do state preparation, you have to actually bring in some kind of feedback. So what that means is that you do a partial measurement, and from that you know where the qubit has gone, and then if you are insisting that you should restrict it only to measurements, then what you have to do is you have to change the angle, the axis of measurement. Because when you typically measure in the same axis as the quantization axis, that's why the projections are along 0 and 1. But you could measure an axis which is along the equator. Then the projections are going to be on this side of the equator or that side of it. Or you can choose any other axis. So as you change the axis, those random motions directions will change as well. So it's possible to do like a feedback process where you're looking at the state and then slowly adjusting the measurement to make the state go from some initial state to some final state. But it will be a very complicated process. But for the purposes of just understanding these processes, people have done these kind of experiments. But you can see that it's a very complicated process. In most cases, in physical systems, it is not possible to change the axis of measurement so easily. It's not a natural norm. In fact, the way we do it is that we actually rotate the state of the qubit to effectively look like the measurement is being done in a different axis. So it's sort of like the Hardeman operation to convert the phase flip into a bit flip and then back. But then to do those rotations, you have to apply a pulse anyway. So then what's the point? You might as well use that pulse to do the same thing. So unless it's a very specific system where the axis of measurement is very easy to control, then this kind of a method might be useful. But it doesn't particularly offer any advantage, apart from the fact that it's very interesting and using quantum mechanical measurements. So it's like a random walk, but you're like slowly nudging the drunkard person to go towards his house, so something like that.
But my doubt came from actually, so gate does nothing but actually plays with the probability amplitude, right? Because the global phase.
But in a deterministic.
Yeah, in a deterministic way. So if it is in a deterministic way and we perform partial measurements onto it, then we could predict at what point exactly per se. So we have two time scales now. At time scale at which the gate actually operates and the time scale at which we measure. So we usually take a path in between this path in between 2 points that we're actually traversing. We cannot determine a continuous path out of it, right? But if we try to determine a continuous path out of it, we could actually presume that a path is always taken in a similar fashion by the gate, which would actually, solve a lot of the problems that comes with noise and error correction. Because now what we have done is actually determine the way a gate acts on the system.
I'm not sure I fully follow the application you have in mind here, but it is not possible to a priori predict what path measurement-induced evolution will take place. I can give maybe an example which might be, in classical physics, which might make it connect. So you take any driven system, right? Let's take an oscillator. You can write down the equation of motion. You can write down what the force as a function of time is, and you can compute how x evolves as a function of time. And if you want x to follow a particular path, you can back calculate what that forcing term should be as a function of time in order to get the path you are interested in. Now imagine that the forcing term is replaced by white noise. You are now asking me, how do I do something from that white noise process so that this will take a predetermined path?
But those don't have coupled inherently, right? Like in a classical oscillator, we have noise and as a coupled wave function to decompose that into actual information that would be used.
Yeah, I mean, for a particular random sequence of noise, you can compute what the output, what the x is going to
So
be.
for every particular gate, we could determine the inherent error that it would bring, right?
I'm not sure I'm following exactly, but what you're saying is not possible. Yes. Anybody else? Let's do a faculty question. Yeah. Well, relaxation processes.
But then why would they make it known on the block sphere itself?
Very good question. So the relaxation is sort of an asymmetric error. I have not discussed that at all. Because I was always saying 0 goes to 1, 1 goes to 0. Relaxation, only 1 goes to 0. Everything goes to 0, 0 doesn't go to 1. So you have to make a small amount of modification to your protocol to account for those kind of errors. There are other encoding schemes where the relaxation error is actually symmetric as well, where you can have rates going in those directions. But the other common type of error is the decaying noise. That usually happens in, say, for example, in superconducting circuits. It happens because the frequency of or the energy level spacing between the ground and the excited state actually fluctuates in time. This happens because of microscopic motion in the substrate. So, for example, the tunnel barrier could have some atom jumping between two locations on some time scale because of quantum tunneling. And because the tunneling process is exponentially sensitive to the barrier thickness, so some atom or some collection of atoms moving effectively means that your transparency of your tunnel barrier is fluctuating with time. That translates to the frequency of the transition fluctuating with time, which can be interpreted because this box plate picture is in the rotating frame of actually omega 0. Otherwise, there is always this Hamiltonian evolution, trivial evolution, if you like, e to the power minus e01 over h bar t, right? So if we usually go into the rotating frame, but now that rotating frame is no longer fixed because you have chosen a particular rotating frame based on the experiments you characterize that omega 01, but then that omega 0 is drifting. So what that means is that if I park the state around here, as the frequency changes, this thing will slowly move around like this. If there was a deterministic jump, then it will accumulate a phase which is going to go around like that. But because this process is random, it will do this, do that, and then that will give rise to a phase error.
But these operations still keep it on the block space, in the sense that they keep the purity of the state.
Yes. Because this kind of motion has to, because it's only changing the phase of the system. There's also some subtlety on thinking about the purity of the state of a single qubit, like exactly what is happening. But it's just, you just have to extend it to the ensemble picture as well. The relaxation processes require a little bit additional treatment to the error correction. I've actually never fully understood that in great detail. But in all of these models, you do assume that. Okay.
So
My question is about the second lecture that we had on the hardware.
Yeah.
So there we discussed this particular electronic circuit which resembles a qubit. And in that circuit you...
Doesn't resemble a qubit. It is a
qubit.
Yeah.
And we made analogies of that particular oscillatory circuit to a quantum harmonic oscillator. But over here you said that this particular oscillator has a certain energy bound. And I want to know where that particular bound comes from.
So it comes from the fact that the circuit model, the mechanical analog of that is actually the pendulum. Okay. So when you have a pendulum, the ground state is with the pendulum just hanging free. Right? And the largest energy you can, potential energy you can give it is when it's 180 degrees to the top. You cannot do anything else because after that it comes back down. So that's what gives the bound. So you can directly, when you say that the restoring force of the pendulum is sine theta, the potential goes as, because force is du dx, so the potential goes as a cosine, and the cosine is bounded. So that's where it comes from. So in the case of the Josephson junction circuit, it comes from a quantity called the Josephson energy, or equivalently the critical current. So this is the maximum current that can flow through the junction before it loses its superconducting properties. So that's the physical quantity it sets the highest energy. And the thing is, the same quantity is actually connected to the inductance. So the inductance of that Josephson junction is inversely proportional to the critical current, and the Josephson energy of the system is directly proportional to the critical current. So the smaller the inductance, the larger the energy, the number of states you can have. It's just that the picture I showed you, that was for a typical case of the kind of inductance we use in our experiments. And they are about to have about 6 or 7 levels in that.
So you said that we should include the 0 to 1 term. Like while mentioning relaxation,
I didn't say that we have to include that. That in some cases, some relaxation camps can give you functions.
but in our example,
The problem is that if I only use relaxation as the channel, then 1 will go to 0. 0 will not go to 1.
but like our reservoir is at 10 millikelvin, so does it actually provide photons that can take like it's almost at 0 Kelvin, right?
Yeah.
So there we intently, like even if we write a quantum optical mass equation, or we consider jump operators which take 1 to 0. But
Yeah. So it doesn't. So these processes don't come from a terminal.
it is not a sum.
I mean, that's the reason. So in order to suppress the thermal processes, is the reason why we do these. These happen to various other kinds of processes. For example, the breaking of copper pairs due to high level radiation impinged on a device because of non-conductivity. There is also a crazy mechanism which actually has been defined as cosmic rays. It's a very rare event, but every once in a while a cosmic ray can actually go through your junction and sometimes it can actually destroy the device. But people, I remember when I was a fairly young graduate student, my advisor had mentioned this, and we all thought that this is completely nuts. But they've actually done experiments, they've actually seen the effect of even radioactive particles in the vicinity of your experiments, on how they affect various coherence properties of your fluids, and then they demonstrated that by putting lead shielding, they're actually able to confuse. So all kinds of crazy things can happen. How do you suddenly you need to put lead shielding on your quantum computer? But see, the probability of these processes are so small that 10 years ago we couldn't even think about them existing because there were 100 other problems which were much worse. So as we are solving all the other problems, these minute processes are slowly coming. For example, the radiation induced breaking of copper pairs was only rediscovered sort of 10 years ago. They had known already in other fields, but in superconducting fluids, they made one dramatic improvement and suddenly the coherence times improved by a factor of 10. But one number did not improve, and we were like puzzled for about a year about what was going on. Then they realized that this was higher and have to include special type of physicists.
So not a question like in the context of photosynthesis, you mentioned that noise can be useful. Noise is useful for the physical process of photosynthesis or for computation.
That simulation verifies that the noise is useful for photosynthesis.
I think,
While after this, just ask questions. Let us be it's okay, maybe we'll take one last one. Yes, people do it. Random use. So, in fact, a qubit prepared in a 50-50 supermodel state and measured is the perfect random number. But there are technical difficulties. Close to 50% you are, that depends on the accuracy of your experiment. And then how quickly and precisely you can measure it also will give rise to how big the random is. So many systems, but this is too expensive a way to create random. There are much cheaper ways, commercial ways now already exist. Quantum random number generators, using light, like lasers and things like that. And it's actually an important ingredient in quantum communication because they need a random source of signal for calculating some of the solutions. So it's actually a commercial buy quantum random. Sometimes as small as something. Okay. All right. Thank you so much. This was a lot of fun.
Thank you, sir, for this amazing talk. I hope this talk and the technologies discussed spark some interest in our young minds and curiosity in our teachers. With that, I would like to call our president, Ram Thapar, for a program.
Okay, so thank you everyone for coming. I've given two of these already, but sort of a more formal one. So on behalf of the society, I'd like to thank Professor John Varghese, our principal, for giving us the opportunity to conduct this event. We're also deeply grateful to Mrs. Popli and to all the Popli trustees and everyone associated with the trust who could not be here today in person but have joined us online for their continued support in helping us conduct this lecture series. We also want to extend our gratitude to Dr. Vijayaraghavan for an extremely insightful lecture which has introduced us to a really exciting and a very new field. Finally, I'd like to personally thank our HOD, Dr. Charan, who is a little bit sick, so he has also joined us online. Dr. Harish Yadav, our University staff advisor, as well as the rest of the faculty for their support. And lastly, the rest of my council, who are again scattered everywhere at the back for some reason. And thank you everyone for organizing the event. I hope you all enjoyed, and please come for the rest of our events. I'd like to call yeah, that's the previous. Yeah, that's at the end. Yeah. Maybe council can just stand up.
No, call them here, call them.
Call, come on here. Everyone come on. Come fast. Yeah. We have Dr. Popli's daughter who is recorded a video. She will not be here with us today, so she would like to say a few words. Following that, Dr. Ishmael will also say.
extended council.
The extended council.
So these are the people actually who have worked out.
Honorable Principal, Chief Guest Dr. Vijayaraghavan, faculty members and friends. It's an honor to speak to you today on the last day of the 27th Dr. Popli Memorial Lecture Series. On behalf of his family, I would like to express my sincere and deep gratitude to the college and the Physics Society for keeping alive the glorious tradition of this annual lecture series. My father, Dr. Popli, liked to bring alive discussions on the cutting-edge research in physics using the beauty of the basic principles. Dr. Vijayaraghavan's discussions on quantum computers over the last 2 days reminded me so much of that. If my father were alive today, he would have really enjoyed these lectures. And therefore, I'd like to thank Dr. Vijayaraghavan and the Physics Society again for bringing the frontiers of research to the classroom and for keeping the memory and values of my father alive. Thank you.
And all captain staff and my society staff advisor to say.
So I think I should thank Professor Raghavan first for accepting our invitation. The original plan was in February, but because of the first year exam, actually, we have to cut down, and I really have to request him to just postpone it, and then we have to rearrange everything, the schedule, etc. Thank you for actually doing all the things.
I was also not very quick at responding. First, it took me a week or so to realize, is this really happening?
And it is really, it's an interesting series in the sense that you have actually explained, presented the entire idea of this complex basically machine, which is still in the emerging basically area. And these 3 lectures, actually starting from the basic and till today, I think everybody got the idea in a very simple way, what is this machine and how it works. I simply relate it actually to the 1950s when actually the industry is transforming from vacuum tube to semiconductors. People are still that time struggling with the challenges how to actually go from these bulky machines which actually covers the entire room, the first ENIAC computer, if you remember. It is so big, it cannot fit a single room. But then this technology evolves, and it took almost 6-7 decades that now the technology is in our pockets. And I'm hopeful that it will not take that much amount of time. We want also to enjoy these things.
My prediction is that it will never enter your pockets.
I can understand because but
no, so the thing is you don't need to. And a good example is things like Alexa and Siri. With the power of the internet, you can exploit the full powers of a quantum computer without it being next to you. Otherwise, everyone would need a supercomputer in their pocket to do voice recognition.
The requirement, the low temperature, the material, and the design, it's all challenging in every respect. Obviously, cannot. But maybe we don't know actually about future. Actually, maybe new technology will come to the So that's all actually. I think I should thank faculty members. While discussing who will be the speaker for this time, we have a list actually, and then actually we come up with yours. Gitanji is not here, but Avina, Gitanji, and Barry sir actually finally zeroed down that we should call Professor Raghavan for this talk.
Thank you so much.
Thank you everyone, and a special thanks to the Physics Society, all these members who actually put in all the effort.
Thank you everyone for joining. I would like to call Dinan Thakur to present the mentor to Professor Raghavan.
So this is the Physics Society Annual Journal for the year 2023. It's got left Okay, so yeah, I hope you all enjoyed. We have refreshments outside. There's pizza today, and but again, before that, we'll do a photo because there's a lot of new people here today as well.
I think they should have a discussion.
Should we do the photo first?
Take it later.
Quickly.
Yeah. Okay, so everybody please collect the laws like yesterday for the photo.
I'll end it, sir. Yes.